Hello everyone, welcome to the tutorial number 22 of IIT-JAM in chemistry, and this is the 8th and last lecture of the physical chemistry chapter, gaseous state. And in this lecture we are going to discuss critical state and law of the corresponding states. Let's begin with the critical state. Critical state means the temperature at the critical state, that is the critical temperature, the pressure at the critical state, that is the critical pressure, and the volume at the critical state, that is critical volume. What about the definition of critical temperature? Critical temperature is denoted as Tc. This is nothing but the minimum temperature required to liquefy a gas, that is the temperature beyond which a gas never liquefies. Whatever be the pressure, if the temperature is above that temperature, a gas can never be liquid, and above the critical temperature a gas is said to be a gas. Otherwise, below that critical temperature it is said a vapor, and vapor can condense into a liquid. So this is the minimum temperature which is required in order to liquefy a gas. Now suppose this gas is kept at its critical temperature, then what should be the minimum pressure? There must be some minimum pressure required to liquefy that gas, and that pressure is known as the critical pressure. This is denoted as Pc. So what about the definition of critical pressure? This is the minimum pressure required to liquefy a gas at its critical temperature, and it is denoted as Pc. And if the gas is kept at Tc and Pc, then its volume of 1 mole amount is known as the critical volume, and it is denoted as Vc. Now these expressions Tc, Pc and Vc can be expressed in terms of the van der Waals constants A, B and the universal gas constant R, and they are related with them as follows. Tc is 8A by 27 Rb. This is equation number 47. Critical pressure is A by 27 B squared. That is equation number 48. Vc is 3B. This is equation number 49. Now the vice versa can also be done, that is A and B can also be expressed in terms of Tc, Pc and Vc. Similarly, the van der Waals constants A and B can also be expressed in terms of Tc, Pc and Vc as A equals to 27 R squared Tc squared 64 Pc. This is equation number 50, and van der Waals constant B is equal to RTc by 8 Pc. This is equation number 51. Now what about the critical compressibility factor? Actually, compressibility factor Z is equal to PV by RT. So if P, V and T are at critical state, then that moment the compressibility factor is known as the critical compressibility factor, and it is denoted as Zc. So the expression of the critical compressibility factor Zc must be equal to PCVC by RTc, and that is equation number 52. And it can be evaluated by putting the values of Tc, Pc and Vc in terms of A, B and R, and as it is like that. Zc equals to Pc, A by 27 B squared, Vc thrice B, R Tc, Tc means 8A by 27 Rb, and its value is 3 by 8, that is in the fraction it is 0.375. Since it is PV by RT, PV has the dimension of energy, RTC also has the dimension of energy, so energy over energy cancel each other, and Zc has no dimension. Next comes the reduced equation of state and the law of corresponding state. If pressure, volume and temperature of a gas are expressed in terms of critical pressure, critical volume and critical temperature respectively as P equals to pi Pc, V equals to phi Vc and T equals to theta Tc, then the van der Waals equation for 1 mole of a real gas becomes, in place of P we are writing here pi Pc, now here plus A by V squared. So A is okay, but in place of V squared we have to write phi squared Vc squared. So here we are writing here phi squared Vc squared. Now this is the P plus A by V square part. Now here V minus B part. In place of V we can here write phi into Vc. So here instead of V we are writing here phi Vc, and minus B is as usual, which is equal to RT, but T is theta Tc, so it becomes R theta Tc. And if we put the values of PC, Vc and Tc as obtained from equation number 48, 49 and 50, then PC is nothing but A by 27b squared, so pi into A by 27b squared. Okay, Vc is nothing but 3b. Okay, so in place of 3b whole squared it becomes 9b squared, so it is, in place of Vc we are writing here 9b squared, and phi squared is present as usual here. Here in place of Vc we are writing here 3b, and hence the equation takes the form in the left hand side like this, and in the right hand side in place of Tc we have to write 8a by 27b, so 8a by 27 RB. Now the RB, this R would be cancelled by this R in the numerator, so R would be vanished here, and finally the right hand side takes the form 8a theta by 27b. So thus this equation takes this form after having put the values of PC, Vc and Tc in terms of A, B and R, and finally on rearranging this we get this form: pi plus 3 by phi squared into 3 phi minus 1 equals to 8 theta, and this is equation number 52. Now what about the significance of this equation? Equation number 53 is known as the reduced equation of state, where pi is called reduced pressure. This is nothing but the ratio of P and Pc. Phi is called the reduced volume, which is nothing but the ratio of V and Vc, and theta is called the reduced temperature. That is also nothing but the ratio of temperature and critical temperature. This equation is applicable to all substances. Do you know why it is applicable for all substances? Because look, it does not involve any gas constants like A, B or universal gas constant R. So it can be applied in case of liquid also. And this equation is of third order with respect to phi. Look, if we look back here, this is definitely of third order with respect to phi. If phi squared is multiplied in both sides, then it becomes pi into phi squared plus 3 into phi cube. So this is the third order equation. Okay, so this equation number 53 is a third order equation, and having 3 solutions. So for the third order equation, this variable must have 3 solutions. Okay, and below critical temperature, one is corresponding to the liquid phase, another is corresponding to the vapor phase. But what about the third phase in the intermediate state? No, it has no physical significance. So this equation is of third order with respect to phi, having 3 solutions below critical temperature, one corresponding to liquid phase, another corresponding to vapor phase, and the intermediate one having no physical significance. For saturated vapor, this equation suffers from the same limitations as does the van der Waals equation from which it was derived. So the van der Waals equation does not satisfy for saturated vapor phase. So this reduced equation of state also fails in case of saturated vapor. That is the drawback of the reduced equation of state. Now what about the law of corresponding states? The law states that if 2 or more substances have same reduced pressure pi and they are at equal reduced temperature theta, then their reduced volume phi, that is V over Vc, that should be the same for all substances. That is the law of corresponding states. So how do you write this law? I repeat, if 2 or more substances have same reduced pressure pi and are at equal reduced temperature theta, then their reduced volume phi, that is V over Vc, should be the same for all. and in this case the substance are said to be in corresponding states. So that's all about this chapter, gaseous state. And finally, let's discuss few questions here. So as continuation from the previous lectures, this is question number 24 in this chapter. First question for this lecture is the value of critical compressibility factor of a van der Waals gas is what? So here 4 options are given: 8/27, 27/8, 3/8, and 8/3. So this is the value 0.375. We know that, isn't it? Therefore, the critical compressibility factor ZC has the value 3/8, and the correct answer is option C. This is the correct answer. Next, question number 25. The volume correction factor for a non-ideal gas in terms of critical pressure PC, critical volume VC, and critical temperature TC, and gas constant R is. So what is the value of the volume correction factor? That is B. And we have found earlier in equation number 51 that this value is nothing but RTC by 8 PC. Okay, this is the value RTC by 8 PC. We know that. So from that knowledge, we can find here the correct option, and option A is the correct answer. And finally, question number 26. This is NTA type question. You have to put the numerical value here for this IIT-JAM questions. It came in 2022, and the question is for a van der Waals gas, the critical temperature is 150 Kelvin and the critical pressure is 5 × 10⁶ Pascal. The volume occupied by each gas molecule should be what in the angstrom cube unit. Okay, and we have to round it off up to 2 decimal places, and few values are given: the universal gas constant and the Avogadro's number. Actually, we know these values, but in the question it's given. So let's find out the answer. So we know the critical compressibility factor ZC equals to PCBC by RTC, and which is nothing but equal to 3/8 for a van der Waals gas. Therefore, VC must have the value 3/RTC by 8 PC. Now let's put these values. In place of R, we are putting here 81314 in the SI unit. TC 150 Kelvin. This is also SI unit. 8 into 5 × 10⁶ Pascal. That is also SI unit. That means the volume should be in the SI unit, that is meter cube. Now this is the volume of 1 mole of a gas, isn't it? So 1 mole of a gas contains this number of gas molecules. So what should be the volume occupied by each gas molecule? So if we divide this volume by the overall number of gas molecules, then we shall get the volume occupied by each molecule. So here in the denominator we add the Avogadro number, 6.023 × 10⁻23. It is a printing mistake. Let me rectify this. This is done. It is 6.023 × 10⁻23, and the unit is meter cube. Now we have to convert this meter cube into angstrom unit. Now we know that 1 meter equals to 10⁻10 angstrom. Then 1 meter cube should be 10⁻10 whole cube angstrom cube. That means 10⁻30 angstrom cube. So if we multiply this whole amount with 10⁻30, then this meter cube unit will be replaced by angstrom cube like this. So 10⁻30 is multiplied here with this whole thing, and then we get this unit angstrom cube, and the final value up to the 2 decimal place, it is 155.29 angstrom cube. So that's all about this lecture. Thank you. And next we are going to start liquid state. Before that, one thing I must repeat here, that you will get all the links of the previous video, the next video, and the complete playlist of this IIT-JAM in chemistry tutorial in the description box of each video. So it is very easy to find out all the videos, and you will get all the links very easily. So thanks once again, and have a nice day.